So let us now, so I end the discussion on broken extremals, and let us now look at another formulation, a very vital formulation of reformulation of Euler-Lagrange, namely the Hamiltonian formulation. Hamiltonian formulation. Okay. So what have we got? We have seen Hamiltonian earlier. So seen earlier. Where have we seen? We have seen in several places, for example, in Beltrami identity, right. So it's not completely new to us. We have also seen when we were describing variable endpoint conditions, and of course when we were using in broken extremals. So H appears in lot of places, right. It seems that this quantity is useful, right, but we haven't explored the full power of the Hamiltonian formulation, right. So this is an alternative, it is an alternative approach, it is an alternative approach to my Euler-Lagrange equation. It is an alternative approach to my Euler-Lagrange equation. We will see that. So the variable H, and why is it that we have to consider alternative approach? Because sometimes using the Hamiltonian approach will reduce the problem significantly or significantly simplify the problem, and further the Hamiltonian approach is coordinate free, right. We will see all these issues. So using so that those are my advantages of Hamiltonian formulation. There is another issue we will see later on, that given one Hamiltonian system, we can construct another one can be constructed, by a special transformation, known as the symplectic map. Okay. So which means that suppose the Hamiltonian formulation is quite complicated in one coordinate system, we can go to another coordinate system via the symplectic map to go towards a much more simpler Hamiltonian formulation, right. So that is also one of the advantages of using Hamiltonian. We can shift from one coordinate to the other, and also we will see later on the search for such a symplectic map, such a map. When I say map, I am talking about these maps. Symplectic maps will lead to a first order PDE, leads to the first order PDE well known as the Hamilton-Jacobi equation, right, or later on as I will say that this is the well known HJ equation. So I am going to talk about all these issues, namely the symplectic map, Hamilton-Jacobi, and so on, step by step. But before that, let me start by introducing what is a point transformation. Okay. So what is a point transformation? So let us build the theory step by step. Point transformation. So a point transformation is a map. It's a map connecting pair of points, let's say small x y, to another pair of points to another pair, let's say capital X y, right. So point transformation is a map from one point to the other, right. Alternatively, we could also have a contact transformation. The point transformation is quite easy to understand. On the other hand, we have the so called contact transformation, which is a function defining the transformation which depends on the derivative of the dependent variable. So I have said lot of things, let me describe in detail. So my contact transformation are functions defining the transformation transformation which depend on the derivative of the dependent variable. Okay. We will see one such very important contact transformation known as the Legendre transformation, and we will use that transformation. So, an example of contact transformation is the so called Legendre transformation. We will see all these quantities, all these definitions immediately. So, my Legendre transform is a contact transform. I denote this as L dot T, right, and we will see that the Legendre transformation provides a link between my Euler-Lagrange formulation and the Hamiltonian formulation, right. This is the link that we are after. Once we have found the solution in one form, that is the Hamiltonian form, we have to change back into Euler-Lagrange form, that is via the Legendre transform. So, let us consider, so to see what are Legendre transform, let us consider a function. So, consider a one variable Legendre transform of y from x0 to x1 to r. Let us say this is a smooth function by a new variable, one variable Legendre transform by a new variable p, such that p is equal to y prime of x. So, this is the definition of the new variable p is equal to y prime x, right. Note that this is a contact transformation because we have defined a function which depends on the derivative of the dependent variable. Here the dependent variable is y, and we have defined the function as the derivative of the dependent variable, right. So, one can potentially be inverted. We can essentially find x as a function of p, provided the second derivative of y exists and it is non-zero. So, one can be inverted to find x as a function of p, right, provided the second derivative of y with respect to x is non-zero, and that is via standard inversion argument. So, we can assume without loss of generality that the derivative is positive, does not matter, right. Okay. Because in this case we are assuming that the shape of the profile is strictly convex upward, or we are assuming a convex shape, okay, of the function. Okay. So, what is p? P is the derivative of the dependent variable, or geometrically it is the slope of the curve. So, p corresponds to the slope, it corresponds to the slope of the tangent line, right. Okay. So, then let us also introduce another new function, namely h. So, we introduce another new function, or the Hamiltonian. So, introduce the Hamiltonian h is equal to minus y plus p times x. I call this definition as my 2, right. Now, it turns out my 1 and 2 are of course Legendre transforms by definition, right. These are contact transformations, and further they 1 and 2 is an involution. What is an involution? An involution is a transformation which is its own inverse, right, or a transformation, we will see how it is. It is a transformation which is its own inverse, right. So, let us see how. So, note that so we can check how it is an involution. Let us see. So, note that del H del P by definition of H. So, note that my x is a function of P. So, it is P which is the independent variable now in this new variable system P comma H, right. So, my del H del P is by definition of H is negative del Y del P plus x plus x well P del x del P, right. So, then this is also equal to minus del Y del x times del x del P plus P times del x del P plus x, or I can club this together. I see that this is also equal to del x del P times y prime plus P plus x. By the definition of P, P is equal to y prime, and I get that this is equal to 0 or this is equal to x, right. So, what I see is that what I have found is that x is equal to h prime P. This relation is very similar to P is equal to y prime x, right. So, in terms of the new variable, x is equal to h prime P. Also notice that minus h of this time h, the Hamiltonian, plus x times P becomes by the definition of h, it becomes this is equal to y, right. And this relation is very similar to saying that h is equal to so h is equal to minus y plus px, right. So, hence we can see that this setup is an involution, right. Okay. So, let us look at a quick example. The example that I have to see how this Legendre transformation work. So, let my function y be equal to x to the power 4 by 4. So, then we see that my P, which is y prime of x, is x cube, and or from here I get that x is equal to P to the power 1/3, right. So, my h, which is equal to minus y plus px, is going to be, so minus y is x to the power 4. So, minus x to the power 4 by 4 plus p is x cube times x, which is also equal to 3 by 4 x to the power 4, or this is 3 by 4 p to the power 4 by 3 by this definition, right. Okay. So, 3 by 4 p to the power 4 by 3 from this definition. Okay. So, then let us see what happens to del h del p. So, del h del p. So, h is completely in terms of p. So, del h del p is 3 by 4 times 4 by 3 times p to the power 1 by 3, which is p to the power 1 by 3, which is also equal to x, right. And minus h plus xp gives me minus 3 by 4 p to the power 4 by 3 plus x. So, x is p to the power 1 by 3 times p. So, p to the power 4 by 3, I get that this is p to the power 4 by 3 times 1 by 4, right, or this is also equal to x to the power 4 by 4 by definition of x, this is also equal to y. So, I see that this definition is giving me an involution, right. So, now let me wrap up this lecture by giving the Legendre transformation with respect to the integrand of the functional. So, let us now consider a more general function. Let us consider f of x comma y prime, which is nothing but the integrand in our functional with in the Euler Lagrange formulation, right. So, let f be a general function where x, y and y prime are considered three independent variables, right, and we define new variables, that is p and h. We define new variables. My variables p are defined by del f del y prime, and my h is now defined to be minus f plus y prime p. Note that the role of y is replaced by the role of f and the role of x is replaced by y prime. Okay? And here in this relation x and y plays passive role, right. They are all implicitly hidden in this definition of the new variable. Okay? And also this quantity is valid provided my second derivative of f with respect to y prime square is not 0, provided this is not 0. Let me quickly look at an example in this category. So, suppose I have that f is the standard arc length integrand of the arc length functional, right. So, then my p is del f del y prime, which is also equal to y prime by 1 plus y prime square under the root, or from here I can find that y prime is p divided by square root 1 minus p square, right. And my Hamiltonian h of x y p is going to be minus f, which is 1 plus y prime square plus y prime p, right. We can replace y prime here and here to get that the solution comes out to be after replacement 1 minus p square under the root, right. So, this is my how I approach normally when we have to perform the Legendre transformation. Finally, I wrap up my discussion by noting that note for the passive variables x and y, the following relation holds, right. So, for the passive variables we have the following relation which holds. Note that since my h is minus f plus y prime p, right, I have that del h del x is equal to the derivative of f with respect to x with a minus, because only f contains x, right. And similarly the partial derivative of h with respect to y is also minus del f del y. So, I have found all the necessary derivative in the Cartesian frame or in the Euler-Lagrange frame to the necessary derivative in the pH frame or the new frame. Okay. So, that wraps up my discussion in this lecture, and in the next lecture I am going to continue our topic of Hamiltonian formulation, namely how to derive the famous Hamilton-Jacobi equation and how is it useful to solve and give us the extremal in another formulation. Thank you for listening.